So we'll just wait probably just about another minute for some more people to join, and then we'll go ahead and start with the review. Awesome. So we'll go ahead and start. So the plan is just to kind of go over some of the practice quiz questions. We'll go over some of the definitions to remember for a bit. And then we have a few more extra problems that we can go over. Or if you all have any questions on past homework assignments or other problems, um, this review is definitely a chance for you all to ask questions that you have and are struggling with. Um, so definitely just let me know. So first we'll go through just kind of refresh some of the definitions, and then we can go through some um, practice problems and questions you all have. So here's just a few things just to kind of like refresh ourselves with um, before we go through some of the rest of the problems. So first, just remembering all the things about functions that we learned, what makes something a function. Um, a function is one-to-one if everything in the codomain is mapped to by some element of the domain, or is specified here that if nothing in the codomain is an output for two different inputs. We have a function is onto if every element in the codomain is the output for some element of the domain. Um, so remember when proving onto, we need to really think about what our codomain is, and we really need to be thinking. You need to just really remember what your codomain is, because the property of onto-ness comes from what you specify your codomain to be, not necessarily just entirely from the function. And then we call something one-to-one correspondence if it's both of those, if it's both one-to-one and onto. Sometimes you might also see bijective. And then remember, we have invertibility of functions. So it's invertible if there is an inverse function. Also, as we went through in some of the lectures, we know that a function is invertible if the original function is a one-to-one correspondence, meaning that we can find such an invertible function. So those are just some of the things to make sure you know. For the quiz, I would have all of these definitions and some others from that we've seen in lecture um, on your little index card sheet that you can have. And then remember, we also have some things about relations. So remember, we learned about finite sets A and B. If you have a function between those and it's one-to-one, then m is less than n. If it's onto, m is greater than n. And if it's one-to-one, m equals n. In other words, if you can find a one-to-one correspondence between two sets, the two sets have to be equal in size. And then we learned about composition of relations. We can also do composition of functions. So remember some of the definitions and how we compute compositions. And don't forget the really three important properties on relations, right? We have something reflexive. Basically, if for all A in the set, A is related to itself. Symmetric, if for all A and B, if A, B is related to itself, then we have to have B, A related to itself. And then for transitivity, if A, B is related to itself and B, C is related, then you have to have A related to B. And then remember, we learned about an equivalence relation if it's all three of those, reflexive, symmetric, and transitive. And then we have some of the special ordering properties. So partial ordering, if it's anti-symmetric, transitive, and reflexive. We have a strict partial ordering if it's antisymmetric, transitive, and irreflexive instead of reflexive. And then a total ordering is something on top of a partial ordering where if for two values that are not equal, if A, B is related or B, A is related, basically so that every pair of distinct elements is comparable against each other in some sort of way, then we say that it's a total ordering. So this is just a little brief refresher on some of the definitions and important theorems that we've gone over. This is not an exhaustive list. So don't only study these definitions and these theorems. Make sure you're still looking at what we went through in lectures and recitation and discussions as well. So then we basically have a bunch of problems from the practice quiz that we can go through. So does anybody have any specific questions or problems on the practice quiz that they wanted to go through together? Okay, so someone says 4, and then could we go over the first one? Sure, yeah, we'll start with the first one, and then we'll definitely hit 4. And then if you have any other questions, just type them in chat for the practice quiz, and we will go through them. So here's the first question from the practice quiz. So we're going to prove a function defined from the integers to the integers, such that f of x is equal to 2x plus 3 is 1 to 1. So how do we prove a function is 1 to 1? Well, we basically have to show that given two inputs, so we let's say a, b, b and z be in our domain. And then we can assume that f of a is equal to f of b. And this is just the assumption we make to prove something's 1 to 1. If fa equals fb, to prove it's 1 to 1, we have to prove that a is equal to b. So if we have fa is equal to fb, then we just do algebra, and we just need to conclude at the end that a equals b. So then we have, so fa is equal to fb. So 2a plus 3 is equal to 2b plus 3. Subtract 3 from both sides. And then now we can divide 2 by both sides. And we conclude that a equals b. So that's a equals b. And f is 1 to 1. Any questions on anything about that, especially the person who asked us to go over this problem on this one? And someone else asked where they can find the slides for this. Yeah, so that was posted in an announcement a little while ago. So if you look the one on review session 9-9, there's a link to the slides for today. Okay, perfect. So that helped. Yeah. Yeah, so just remember when proving 1 to 1, the structure of the proof is always the same. We let two elements be in the domain, assume that f, the function, maps those two values to the same thing, and we just have to prove that a equals b. So 1 to 1 always kind of looks similar. What about would this function be an onto function? I know it doesn't ask us that, but would this be onto as well? Okay, so we have someone saying yes. Okay, so we have a couple saying yes. What about everybody else? If you just want to type yes or no in chat. Would this function be onto? Yeah, so let's think about it. So Sure. Yeah, we can try it. Let's try. So we have a lot of saying yes. So let's try to prove that it's onto. So to prove something's onto, right, we just have to show that every element in the codomain is mapped onto by some element from the domain. So let's let y be an element of z. And then we want to find some x. And let's just assume for some x, let's say that f of x is equal to y. And let's find out what this x is that maps to y, and if it is in fact in z, because it has to be from the domain. So we're just assuming that this exists. We don't know if it's an integer, could be a real number, could be imaginary. We're not sure yet. So if we have, let's try to see what we get for this value. So if we solve this, we'll get x would be equal to y minus 3 over 2 would be the value that would map. So in other words, we've shown that f of y minus 3 over 2 would be equal to y. We found this element that maps to y. Is this element an integer always? Y minus 3 divided by 2 for any y in z.
No, right?
Yeah, no. So this, yeah, it's not always an integer. For example, when y is equal to 2, this would come out to negative a half. So this function is not onto. And if we wanted to give, do I have more room? I don't have more room. I'll write it over here. If we wanted to give like a specific counterexample, we could say, consider y equals 2. F of, what did we just show? Negative 1/2 is equal to 2 times negative 1/2 plus 3, which is equal to 2, but negative 1/2 is not an element of z. So not onto. So if we wanted to prove this by just a counterexample, what I wrote there would be sufficient. We found some element in the codomain that is not mapped onto by an element in the domain. So any questions on that? Perfect. So somebody asked if we could go over practice quiz question 4. So let's do that one. Okay, so here on this problem, we're going to prove or provide a counterexample to the propositions below. So we've got this relation R on S that has all of the integers from 2 to 12. And R is the relation where AB is in the cross product of S cross S, where A divides B. And so then we need to decide if it's reflexive, antisymmetric, transitive, a strict order, or a partial order, or total order, and then draw some diagrams. So let's think about this for just a sec. So to show that this is or is not reflexive, we need to think about if we can show that. So can we show for any x in S that x comma x is in R? So let's think about this first, because this problem doesn't tell us whether or not we need to prove it or provide a counterexample. So we need to kind of think about it and figure out if we believe that this is true or not true first. And then we can prove it. So does anyone have any ideas for part A, whether or not we think this is reflexive? Okay, so we have someone saying yes. Any intuition? Why do we think it might be reflexive? Yeah, someone says it is. Yeah, so anyone want to give a little explanation for why they think it's reflexive? Yeah,
Doesn't
so those were great.
oh,
Oh, yeah, go ahead.
I was gonna say, doesn't S cross X just mean that you take like every combination of the things in the set, so then there would be like 2, 2?
That is, yes, we would have that in the cross product, but we also have the condition that A has to divide B for the pair AB to be in the set.
Oh,
So
well,
2,
it
comma
would.
2.
Well, does that just mean that it has to divide it in general, or like it has to divide into a whole number? Is that what that means?
Yeah, that's what divide means.
Okay.
Remember, divide means if A divides B.
Yeah, so like 4 divided by 4 would be 1, so it'd be good, right?
Yeah. Yeah, so it would be reflexive. Yeah, so A divides B, that means that B is equal to A times K, where K is some integer. And yeah, so we also had some good comments that any number divides itself, which is correct. So let's prove this, that it is in fact reflexive. We figured out we think it's reflexive. Let's show it. So let's let X be an element of S. Then we have X comma X is in the cross product, just by definition. And also X divides X. So X comma X is in the relation, and thus R is reflexive.
Is there like a theorem for why X divides X that we could like mention in the proof?
It's not really like a theorem that we've kind of gone over. You could show it's more. Yeah, I guess you're saying, oh, do we need a little bit more work to prove that? And I mean, we could. So we could add that X is equal to 1 times X. So thus, by definition, X divides X. Would be a little bit more explanation, but for this, it's just fine to say that X divides X, because this is such a kind of trivial thing. It's mostly just by definition that X divides that any number divides itself. So yeah, it's reflexive. Now let's think about antisymmetric. So for antisymmetric, remember, there's a couple of ways to think about it. But one way is if we have some, let's say A not equal to B, and AB is in the relation, then BA can't be in the relation. I find this to be the easiest way to kind of think about antisymmetric. Just where if AB is in the relation, you can't have BA in the relation, unless the relation was reflexive, is what this says. So any thoughts on whether or not we think that this would be antisymmetric? Oh, yes, this has to be true for, yes, that's a really good question, for all A and B. Yeah, really good question. Okay, so we have some people saying not antisymmetric. Why do we think it's not antisymmetric? Any kind of explanation?
Isn't by definition of cross product won't B comma A exist in the relation?
Yeah, so from cross product, yeah, all the combination of pairs
Hmm.
will be in the cross product. So if you had 2, 3 in the cross product, 3, 2 will be in the cross product.
Right.
But to be added to the relation, we need the added constraint that A divides B. So we're looking at all of the elements of S cross S where A divides B. And if that happens, then the pair, the tuple A comma B, is in the relation. So yeah, so does anyone have, so for the two who put in, yeah, any other ideas for why this wouldn't be anti-symmetric?
Could we just do a counter example and prove that it's not an integer? Oh wait, no, this isn't an integer proof, huh?
Yeah, to prove that it's not anti-symmetric, you just need to find two tuples. So you need to find, for some A and B, you need to find an A, B in R and a BA in R where A doesn't equal B in order to prove that it's not anti-symmetric. Yeah, so okay, so somebody has an example. So think about 4, 2, and 2, 4 is what they're saying. Does this prove that it's not anti-symmetric? Well, we definitely have 2 divides 4 because 4 is equal to 2 times 2, and 2 is an integer. But does 4 divide 2? No, 4 doesn't divide 2 because 2 would be equal to 1/2 times 4, and this is not an integer. And it actually is, yeah, go ahead.
Do A and B have to be distinct? Could you do like 2 comma 2?
You couldn't have to be distinct. So
Okay.
remember, from anti-symmetric, we say that A can't equal B. We allow for reflexivity. So the relation can be reflexive. Or we're not going to consider that. We're looking at anti-symmetry. So this is actually, so it is actually anti-symmetric. And this is kind of the intuition why, because for any pair where the elements are distinct, like we just went through 4, 2, and 2, 4, those don't divide each other both ways. So let's prove that. So for anti-symmetric, let's let xy be an element of S such that first we have that x is not equal to y and xy is in R. And then we need to conclude somehow that yx is not in the relation. So if xy is in the relation, then that means, by definition of the relation R, that x divides y. And since they're not equal, so since x doesn't equal y, it can't be the case that y divides x. X divides y and y divides x implies that x is equal to y. So since we don't have that case, this can't happen. Thus why x is not in R, and therefore R is anti-symmetric. So any questions so far on anything we've been proving here? Okay, so we did reflexive, we did anti-symmetric. So now let's think about, would this be transitive? And right, remember for transitive, running out a little bit of room here, but for transitive, all we're saying is that if for all A, B, C that are in our set, if A, B is in R and B, C is in R, then that implies that AC is in R. So do we think that is the case? So in other words, for these tuples in S cross S, do we think it's the case that if A divides B and B divides C, that A divides C? Any thoughts on that?
Do you just have to find one example where it works, or do you have to find that it works for every single value in it?
Yeah, really good question. So when we're proving something is true, like a property like this, we have to prove it's true for any possibility.
Okay.
So we have to show for all ABC that are in the set S that this holds. But if we wanted to prove this was not transitive, so to prove something doesn't have a property, you just need to find one time when it doesn't work. And that's enough to show that that property doesn't hold. Okay, so we have somebody thinking that yes, it's transitive, and then somebody else asks, can a set be both transitive and anti-symmetric at the same time, or is that impossible? Yeah, really good question. And this problem will answer that. So yes, this in fact is transitive. And that also answers your question in that we are going to have a relation here that is reflexive, anti-symmetric, and transitive. So let's kind of look at why. Why is this transitive? So to prove transitivity, we just need to let their three elements be given. So let x, y, and z be an S. And then for transitivity, we assume that x is related to y. So x, y is in the relation, and y, z is in the relation. And then we need to do a bunch of work, conclude that x, z is in the relation. So what does it mean that x, y is in the relation? Well, for x, y to be in the relation, that means that x divides y and y divides z. Now, in order to prove this, we'll need to look a little bit more at the definitions of these. So by definition, y is equal to xk, where k is an integer, and then z is equal to some yj, where j is an integer. And then somehow we need to conclude that we want x to be xz to be in the relation, so we need z to be some integer times x. So how can we show that? We want z equal x for some like m or something. That's what we want to conclude. And if we know this, then we know that x divides z, so x comma z is in the relation. Well, we can do a little substitution here. So we have y is equal to xk and z is equal to y. So what we can do here is, well, then z is equal to x times k times j. And then we can say that z is equal to x times m, where m equals kj. And m's an integer by closure. So thus, z is equal to x times m, so it's a multiple of some integer. So thus, by definition, x divides z. So we have that xc is in the relation. Therefore, R is transitive. So any questions on that?
I have a question.
Yeah, go ahead. I couldn't quite hear you. If you want to turn up your mic a bit.
Remind me how you got z equals xkj.
Oh, yeah, good question. So what we did is we knew by definition that y was equal to x times k. And then we know that z, by definition, is equal to y times some integer j. So I just did a substitution. So I substituted y equals xk here.
Oh, okay. Thank you.
Yeah. Any other questions? Awesome. Okay, so we've done the first three parts. So we've proved it's reflexive, antisymmetric, and transitive. So now we need to think, is R a strict order on S? So does anybody remember what it meant for something to be a strict ordering?
It's anti-symmetric, transitive, and irreflexive. Was it? Or
Yeah. Yeah, so it needed to be antisymmetric, transitive, and irreflexive. And so somebody says, yeah, so it requires irreflexive, so it's not a strict order. And that is the perfect idea. It is not irreflexive. And the reason it's not irreflexive is because it, in fact, is reflexive. We proved in part A that for any x in the set, it's related to itself. So for part D, no. R is not irreflexive. And we could prove this by just a brief counterexample. We can explain that it's also not reflexive, but if, let's say on a quiz you were being asked to prove something was just irreflexive in and of itself, or not irreflexive, we can show this by saying, consider the element 2, that's an element of S. 2 comma 2 is in the relation since 2 divides 2. So thus we found some element that's related to itself. So thus R is not reflexive. Irreflexive. Also, remember that these are not complete opposites of each other, that irreflexivity and reflexivity are not opposites. So you can have a set that is not irreflexive and is not reflexive. So just remember this. So just because you've proved something is not reflexive doesn't mean you've proven that it's irreflexive. A set can have neither of those two properties. And then, so we think we had just one last part. If we scroll back up to our questions. Okay, and then we needed to ask if R is a partial order or a total ordering. Oh, somebody had a question first. So would that also be the same for symmetric? Yes. So symmetric and antisymmetric, they are not opposites of each other. You can have a set that is neither symmetric nor antisymmetric. So just remember that. And the reason why this happens is because, like, for both of these properties, reflexivity and irreflexivity, it has to hold for all values. And same with symmetry and antisymmetry. We're required to hold for all values. So if you have a set where it only holds some of the time, that's where you get or a relation where it holds only some of the time. That's where you kind of get relations that are neither of those things. Yeah, so good questions. So, does anybody remember what the definition for partial ordering is. So if we want to figure out that R is a partial order, or if it's a total order. So first, let's figure out, is it a partial order? Yeah, so somebody said yes. So RAT, yes, it has to be reflexive, antisymmetric, and transitive for it to be a partial order. So is R a partial order? Yes. It's both reflexive, antisymmetric, and transitive, because that's the first three properties that we proved. So it definitely meets the definition of partial order. And then remember, total order is a little bit more involved to prove total ordering. And so let's kind of, we'll go over that. And then since it's a partial order, then we'll need to draw the Hasse diagram. So let's figure out next if it's a total ordering. So remember that a total ordering is a partial ordering. Where for all AB, and in this case will be an S, if A doesn't equal B, then either AB is an R or BA is an R. So basically every element, if you take any two elements, they have to be related in some way. So do we think that's the case with this relation? Do we think that for any two elements that are not equal, we can show that they're related to each other in some way, either AB or BA? Yeah, so somebody says no, and that is definitely the right idea. But why? So let's think about that with a brief example. Let's consider 2, 3, and S. Neither 2 divides 3, nor 3 divides 2. So we found two elements that are distinct, interset, and neither of them are related. So that meant that 2, 3 is not in the relation, and 3, 2 is not in the relation. So R is not a total order. Okay, and then now we need to figure out how to do the Hasse diagram. So remember the Hasse diagram, we use that on partial orderings. We eliminate any arrows that go to themselves. We also eliminate using any arrows, and we just draw lines. And then we draw lines from elements that are smaller to elements that are larger. And the reason why we do this is because a Hasse diagram implies, because we only do it for partial orderings, we can figure out some partial way to order our relation using this. So let's start with the smallest elements, because they'll always be kind of, if we think at the bottom. So for 2, right, what are all the things that 2 is related to? In other words, what are all the things? Let me just recall. Let me write what the relation is again. So what are all the things that 2 would be related to? Yeah, so somebody says, yeah, all the even numbers. Yes, so it would be related to all the even numbers. So we definitely have 2 being related to 4. 2 is also going to be related to 8. But remember, with Hasse diagrams, we kind of have these relationships that 2 is related to 4 and 4 is related to 8. So we write it in this manner. Right, what else do we have? So we have 2, 4, and 8. we'll have some 6 that'll be separate, that 2 will be related to. We also have, and we got 8, we'll have a 10, 2 will be related to, and then we have a 12. So the 12, we can put here anything that's related from 6 is related to 12. We also have 4 being related to 12. So 2 is related to 4, and 4 is related to 12, 2 is related to 6, 6 is related to 12. So that's kind of how we show these. Oh, yeah, great. So question. Somebody asked about 1. So the set S that we're looking at is, it starts at 2. And then it goes up to 12. It's a really good question. If that had been the case, 1 would have been related to everything. And it would have been at the very bottom of the Hasse diagram. And then we'd have had a bunch of arrows going up. So these are all the things kind of for 2. For 3, we'd have 3 is related to 6, and we can place it here. And then it'd also be related to 9. We got 4, 5 would be related to 10. And then 7 and 11 are out over here, not related to anything because, yeah, nothing in our set S is divisible by 7 or 11. So this is what we would have for the Hasse diagram. So any questions on this problem? This is a really detailed problem. Covers a lot of material on sets and relations and orderings that we've been talking about. So any questions?
Should we anticipate a problem this long?
This long? No.
Okay.
We have taken into consideration some of the complaints that we got on the previous quiz for it being a little bit too long. So we have tried to shorten down some of the problems. So that way it should hopefully be quite doable within the 60-minute time limit. But definitely parts of this problem you could anticipate. Proving something's reflexive, antisymmetric, transitive. You should all be very comfortable doing that. And even the other parts, proving it, strict ordering, partial total, and drawing a Hasse diagram. Definitely all things in this problem you should be comfortable with. It probably just wouldn't be jam-packed into like one question. We would spread it out just a little bit. So there's not as many as questions that are time consuming. So somebody asked how many problems will the quiz have? It'll be a little bit shorter than previous ones. I think it's like 5 or 6, and then some of them have multiple parts. Something around, it'll be similar. The number of questions will be similar to what you've seen before, but we've tried to make it so that each of the questions takes a little bit less time than it did the last time. Okay, and then somebody asked, could you explain this Hasse how to draw this Hasse diagram a little bit more carefully, or more generally? Excuse me. Yeah, the Hasse diagrams definitely are tricky. So let me first kind of explain. Do I have another slide here? I don't. Okay. So for Hasse diagrams, right? Let me just erase the rest of this because, yeah, let me, not that. Okay. Can I not select? Okay, oh, that works. Okay, we'll put this over there so we can still see the diagram. But yeah, so what we do with Hasse diagrams. And kind of the rules. So they're only for partial orderings. So for us to draw a Hasse diagram, we need to make sure first it's reflexive and asymmetric and transitive. Then we don't add any loops. And why? Because we already know from the first part, it's a partial ordering. We already know it's reflexive. So it'd be quite redundant to go and draw all these self loops. So for simplicity, the Hasse diagram ignores that. And we just say if it's a Hasse diagram, we know that it's reflexive. We know that everything is related to itself. So when we're drawing the diagram, we don't do that. The other thing to remember is we're only using line segments. And we have that the direction of the relation is from a lower node to a higher node. So the direction, like in this example, the direction is always from 2 to 4. So it's always kind of going up like this, except we just start putting the arrows in. And we do this because we know it's not anti-symmetric. Because we know that it's anti-symmetric, so that's why we can just like ignore the arrows and kind of form this ordering, because we know we don't have arrows in reverse in any place. And then the other rule is we only draw a segment from A to B if AB is an R, and there is no C, I guess I'll put this kind of like between A and B. So in other words, like for this example here, we don't draw a line from 2 to 8 because 2, 4 is in the relation and 4, 8 is in the relation. So 4 is between 2 and 8 here. So we don't draw the line from 2 to 8. And the reason why this works out is because it's transitive. Right? We only draw Hasse diagrams for ordering, so we know transitivity applies. So we know that if we have an arrow from 2 to 4, we know that 2 is also related to 8. So these are the rules kind of for drawing Hasse diagrams. So when you're drawing them, I guess let me explain maybe a little bit more kind of the thought process behind this. So what I always like to do, I always like to start at the smallest elements, because you know those are going to be on the lowest order, the lowest level of your diagram, right? So if you start with the smallest element, that makes sense for your relation, right? We're relating A to some B, so we're starting with the smallest element 2. Then you just need to figure out what element 2 is related to, and then what else if those elements are related to anything else. So you can maybe even go through a process something like this. So whenever we're at a bottom level, we're always drawing nodes up. We never draw them sideways. If we have a relation between like 2 and 4, we move it up to a next level, because the line segments are always going up from lower levels to higher levels. So we'd go from 2 to 4, 2 to 6, and then we could do 2 to 8. And we could write it this way and then do a bunch of erasing later. And then if we figure out what is 4 related to anything, well, 4 is related to 8, so I have to take this out. And 4 is related to 12, so we have to take this out. This could be one way you could think about drawing these. And then we need to start with 3. What's 3 related to? Well, 3 is related to 6. And it's also related to 9. And then it's also related to 12. But 12 is already up here. And 6 is related to 12, so you draw that line there. We've already got 4 and everything. 5, only thing is related to 10. And then we just finish. Everything that's not related just goes on this bottom level. So here we've kind of got these 3 levels. And then this is the structure that we use for the Hasse diagram. Does that help clear up some of the confusion on drawing these? And if not, please let me know. So has that cleared it up, hopefully? If not, please tell me. This is the perfect time to say, no, that this doesn't make sense. Okay, yeah, so somebody has a question. Can we exchange the order in the same level? Oh, perfect, yeah. So certainly. You could, so I could put like 7 and 11 here, and then I could put 5 here. It's just a little bit easier to look at if everything's in order this way, like numerically. So you can say I drew it here. Everything's just in order numerically. It makes it a little bit easier to understand if you need to use the Hasse diagram. But no, the order on a line on the same level doesn't matter. It's just the arrow relations and the order above that does. Awesome. Any other questions on these Hasse diagrams? And if not, any other questions on the practice quiz anybody wanted to go through? Okay, perfect. So somebody says, okay, question, and that clears it up. Perfect. So somebody says question 9. Yeah, so let's take a look at question 9. Okay, so we're looking at the same set again. We've got this set of integers from 2 to 12. And then we've got this relation R on A, where this relation R is defined by the set of all AB that are in A squared, where A and B have the same set of prime factors. And then it gives us an example. So 2 and 8 have the same set of prime factors. 2. Why did it have the same set? Right. Well, 2 is equal to 2 to the first, and 8 is equal to 2 to the third. Sets don't include repetition, repeated elements. So the set of prime factors is just 2 for both of these. And then 2 and 12 do not have the same set of prime factors. Why? Well, 2 is equal to 2 to the first, but 12 is equal to 2 to the second times 3 to the first. And so thus the set of its prime factors are the set 2, 3. And then we want to prove that this is an equivalence relation, or give a counterexample if it's not an equivalence relation. And then if it is, we need to figure out what the partition is. And then somebody has a question, is A yes? So A squared is the same as just A cross A. Just a little shorthand if you're looking at the same set. Okay, so if we want to try to figure out if this is an equivalence relation, what are the 3 things we need to look at? Or the 3 properties it would have to be an equivalence relation? Right, so for equivalence relations, right, we need to figure out if it's reflexive, if it's symmetric, and if it's transitive. If it meets all 3 of these, it's an equivalence relation. If it fails one of them, it's not an equivalence relation. So let's just go through these one by one, and we'll figure out if it has each of these 3 properties. So first, for reflexive, do we think that this relation is reflexive? Any thoughts on this? Okay, yeah, so we have some people saying yes. Yes, it is. It is reflexive. And right, because what are we putting in the relation? Well, we're putting in all the elements A, B that have the same set of prime factors. And if somebody has an example, yeah, 2 has the same prime factors as 2. For any number, it has the same prime factors as itself. It's a little bit trivial, and this proof is going to seem a little bit trivial, and but it's really just because just by definition this happens. So let's let A be an element of our set big A. Then A has the same prime factors as A. Right, it has to. So it's in the relation, and thus R is reflexive. And then what about, so next we need to think about symmetric. Do we think this relation is symmetric or not? So in other words, if AB is in the relation, do we also have that BA would be in the relation? Yeah, somebody says yes. Yes, we would have that. Again, this is kind of just by definition. So let's let AB be in the set big A. For symmetry, we let AB be in the relation. To prove it's symmetric, we have to prove that BA is in the relation. So if AB is in the relation, then A and B have the same set of prime factors. Thus, B and A have the same set of prime factors. If A and B did, then B and A must. So thus, BA is in the relation, so R is symmetric. This, again, very straightforward. It's primarily just because of definition and because of the English use of the word and being commutative. So if A and B, then B and A. And then next we have to prove whether or not it's transitive. So do we think if A is related to B and B is related to C, that A is related to C for this relation? So if A and B have the same set of prime factors, B and C have the same set of prime factors, do we think that A and C have the same set of prime factors? And yes, we have some people saying yes, and that is correct. It will have the same set of prime factors. So let's let A, B, C be an A. And, oh, I should have put, instead of a then there, and AB. Because when we prove symmetry, we just assume that A is related to B. And for transitivity, we assume that A is related to B and B is related to C. We can prove this one a little bit more formally. So let's let so we're just going to call it big P, big Q, and big S. We generally use capital letters for sets. So these are going to be sets of the prime factors of A, B, C, respectively. So P as the prime factors for A, Q as the prime factors for B, and S as the prime factors for C. So then if A is related to B, so then P is equal to Q, and Q is equal to S. Just by definition of AB being in the relation and BC being in the relation. And if AP equals Q and Q equals S, so then P must equal S. So P and Q are the same set. In other words, A and C have the same set of prime factors. So AC is in the relation. Thus, it's transitive. And since we proved all three of these, we proved it's reflexive, we proved it's symmetric, we proved it's transitive. Thus, it's an equivalence relation. So now that it's an equivalence relation, we need to figure out the second part. What's the partition of A induced by R is. But before that, anyone have any questions over proving any of these statements reflexive, symmetric, or transitive for this relation? No? Okay. So now let's try to figure out what the partition of A induced by R is. Because remember, if something's an equivalence relation, that means that we can create a set of partitions for the space that we're for the set we're looking at. So let's try to figure that out. If I can get to the next page. Okay, so let me remind you. So we've got A. And then remember, for our relation R, we have that AB is an element of A squared, where A and B have the same prime factors. So basically, we need to figure out which elements are related to each other, which means we need to figure out the prime factorization of all of these numbers. So 2 is equal to 2 to the first. 3, that's just 3 to the first. 4 is 2 squared. 5 is 5 to the first. 6 is 2 to the first times 3. 7 is just 7 to the first because it's prime. 8 is 2 to the third. 9 is 3 squared. 10 is 2 to the first times 5 to the first. 11 is just 11 to the first because it's prime. And then 12 is 2 squared times 3 to the first. So in other words, so we've got the prime factorization, so let's look at the sets. So we might have like a grid here. So this is the prime factorization. And then what are the sets for these? So it's just 2 is just the set. It's the set of prime factors, just the set 2. The set 3, this is just the set 2. Set 5. Set 2 comma 3. Set 7. Set 2. Set 3. Set 2 comma, that's a 5. Set 11. And then we have for 12, a set of 2 comma 3. So we've got all of these elements. So who do we have related to each other? And then I guess this can be our partitions. So one of them, let's look at all the things that have just the set 2. So for one of ours, we've got set 2. We've got the element 4 and 8. Then for the elements that just have the set 3, we've got 3 and 9. Those will just have the element 5 is just 5. Those with the set 2, 3. So we've got 6 and 12. For the element 7, just a 7. And then for the set that have 2, 5, that's just 10. And then for the sets that just have just the element 11, that's just 11. So these are the partitions. For A, why are they partitions? Well, because if you take the union of all of these, we get the set A. And all of these are distinct sets. No element appears in either one of these partitions. And we're guaranteed that because it's an equivalence relation. Equivalence relations guarantees us that we can form this type of partition on a set. Any questions for this part, for how we figured out what the partitions were from the equivalence relation?
Where did the 6, 12 come from?
Oh, because 6, its set of prime factors is 2 and 3, and 12 set of prime factors is also 2 and 3.
Oh, okay, thank you.
Mm-hmm.
What's stopping you from like creating a combination with a set that isn't necessarily like what you put here? Like what if for 8 you did like 2 squared plus 2 squared, something like that, instead of 2 to the third? Like that's just an example, but like, are there like cases where you have to choose the correct combination of numbers to get the right set? Does that make any sense?
Yeah, that makes sense. And the reason why we don't is because the prime factorization for any number, for any, I'll preface this with positive integer, is unique. So there is one and only one prime factorization for every positive integer. The same is true for the negative integers up to multiplying through by a -1, by a negative. So yeah, so this is why we're guaranteed. We can't mess it up because the prime factorization is unique. Because like for what you're talking about with 8, we couldn't have 2 squared times or plus 2 squared, because the prime factorization tells us that for any integer is a product of primes. And that comes us from the fundamental theorem of algebra, that any integer is a product of primes, which gives us these prime factorizations that are guaranteed to be unique. So yeah, good question. Any others on this problem? Awesome. So we've been going for about an hour. So we can give everybody a little bit of a brain break. Let's go ahead and take a break for like 3 minutes, and then we'll come back and finish off the rest of the 45-ish minutes and go through some more practice problems. So let's just take a 3 minute. I'll be back in like 3 minutes, and we can all take a little bit of a break and then get back to finishing the rest. Awesome. So hopefully when it's able to feel a little bit re-energized to finish this last little bit of the review. So we can either continue with some more practice quiz problems. We have some additional problems that we could also go through that I picked out. Or if you have any questions on problems you've seen in the textbook or on the previous homeworks, really anything you want to see. So please just let me know if there are any questions you want to go over from either the practice quiz or homework. And if not, we can do some others. Okay, yeah, so someone's saying more through the practice quiz. Sure, any problems in specific on the practice quiz? Yeah, so anyone have any problems specific on the practice quiz? If not, we can go through the rest that we didn't prove thus far. Okay, then someone says additional problems. Yeah, so if you have a specific question, so if anyone has a specific practice quiz problem they want to go over, let's go over that. And then if not, we could hit some of these extra problems that I've picked out. Since for all the practice quiz, we do have the solutions posted as well. But yeah, if there's any specific questions on the practice quiz that you want to walk through or need some more explanation on, please just type it in chat. Okay, someone else saying extra problems. So yeah, the one who asked for a more practice quiz, if you have a specific problem, just shout it out. Okay, so somebody says the practice problem 8. So let's go through that one. And then if no one else has any practice quiz problems, we can do some extra problems after this. Okay, so this problem, we've got this set A from 1, 2, 3, and 4. And then we've got functions f and g that are defined where f's domain is mapping from A to A cross A. The rule that f of A is equal to A comma A. And then we've got the function g from the cross product of A and A just to the set A with the rule that g of x comma y is just x. We just take the first element of the tuple. We need to prove are they inverses of each other. And then prove whether they are. So let's figure this out first. Do we I guess actually it's a little bit hard to see whether they are inverses. So let's try to prove both of these. And to prove that, what do we have to do to prove two things are inverses? Well, we basically have to show, right? We need to show that G compose F is the identity function over just the set A. And why? Because G maps, so if we're looking at G composed F, recall that G composed F is just G of F of X. Or F of A, I guess, so we're talking about elements of A. And so F takes something from A to the cross product, G takes something from the cross product to A. So we need to show that this is just the identity of A, right? It just maps every element in the set A to itself. And then we will also need to show that F composed G is the identity for A cross A. And recall that F of G of, I guess it should be a little bit more formal there, like that. Of AB is just f of g of AB. And recall that G takes something from the cross product to the set A, F takes something from the set A to the cross product. So this is just mapping cross products to cross products. So we need to show that it maps everything in A cross A to itself. And if both of these cases hold true, they're inverses of each other. So let's try to show this first part. So what do you have to show? So we're going to let some element A be an element of the big A. And then we're just going to define the identity function. I of A, which takes elements A and just maps them to itself. So it just basically spits out the input. It's just the identity. So then if we look at G composed F of A is G of F of A. F of A, what does F of A do? F of A takes an element A, it maps it to the tuple A comma A. So this is G of A comma A. G just takes the first element of the tuple, so it returns A. And this is just equal to what the identity element gave us. Thus, G composed F is the identity. So we've shown this part. That doesn't mean it's one-to-one yet. We have to show it for the other way. That F composed G is the identity. So do the same thing. So let A be an element of the set A. And we're going to define the identity function for A cross A. Just takes a tuple A comma B and just spits out the tuple. That's just what identity functions do. So if you look at F composed G of A, that's just F of, A comma, let A B be in the set A. We need to look at two elements here because the domain of this is the cross product of A and A. So we need to be looking at the tuple. That'll be F of G of A comma B. What does G do? Well, G just takes the first element of the tuple. So this will be F of A. And then what does F do? Well, F takes element A, and it just gives out the tuple A comma A. So this is equal to A comma A. But this is not equal to A comma B. It's not equal to the identity of AB. So F composed G is not equal to the identity. So F and G are not inverses. So to show something as an inverse, we had to show both of these. You have to show that G composed F is the identity. F composed G is the identity. This is true for any function. We showed that G composed F was the identity function, but F composed G was not. So they're not inverses of each other. Any questions on this or proving anything about inverses?
What does identity function mean?
Yeah, that's a really good question. So the identity function is just any function that maps elements to themselves. So whatever the input is, that's the output. So that's why we defined the identity over a set A, where we're just looking at single elements, to just be A. So it takes an input A and it just returns that. So it just maps the input to the same thing. And that's also why when we did A cross A of AB, it just returns AB. So it just takes the input and uses that as the output. So it maps every element just to itself.
Thank you.
Yeah, no problem. Any other questions? Okay, so somebody asked, do identity functions have one-to-one correspondence? So are they both, in other words, are they both one-to-one and onto? Yes. They're both one-to-one and onto. As long as you like don't do anything weird with like the domain and codomain, for example. So I mean, yeah, but they're one-to-one and onto, just by as long as like the domain and codomain are the same thing, which is what you define an identity function as anyway, because it just maps every element to itself. Then it'll both be one-to-one and onto, just by definition. And so somebody else says, so a function composed by its inverse should be equal to the identity function. Yes. So f of f inverse, if I have another page, f of f inverse of x should be equal to x, and f inverse of f of x should be equal to x in general. If both of these two things hold, then f inverse is definitely the inverse. Yeah, good questions. Any other questions on this problem or inverses? Awesome, don't see any. Did anyone else have any other practice quiz problems that they wanted to see? If not, we'll go on to some extra problems. So I don't see anyone who has any practice quiz problems. So we can just go through some extra problems then. If you have questions, remember the practice quiz solutions are available online as well. So for the problems we didn't go through, those are available. The earlier review may also have gone through some of them if you wanted some other explanations on problems as well. So let's look at what extra problems we have. Okay, yeah, so here's one. So we've got this set A1, 2 that contains just the elements 1, 2, 3, 4, 5. And then we're going to write out the relation R that expresses greater than on A. And then we want to figure out, is R reflexive? Is it anti-reflexive, symmetric, anti-symmetric, or transitive? And if a property does not hold, we need to figure out why. So let's first try to figure out how to construct this relation. All right, we'll just be doing it element-wise, so we'll just be creating the ordered pairs. Or just the pairs of elements. So let's figure out what's in the relation R. So it's a set of all tuples where And if this is maybe not as quite as clear as greater than, so we're basically saying that R is the set of all AB, or AB are in A, and A is greater than B. So what elements do we have? Well, certainly we have 5 is greater than 4. So it's in the relation. And 5, 3 is in the relation. 5, 2 is, and 5, 1 is. And then we've got 4, 3 in the relation. 4, 2, and 4, 1, and 3, 2, 3, 1, and 2, 1. And those are all the elements. So for example, we don't have 5 comma 5 in the relation because 5 is not greater than 5. And then I just wrote it out in this way, so it's kind of easy. We don't forget any element because we just started with the largest element and then basically paired them up with all the elements smaller than them. So anybody have any questions for how we write out this relation? Or does this kind of make sense?
In general, would you recommend that we write out a relation like this?
Well, it only makes sense in this case because the set A is finite. So we actually can write out the entire relation. So this is the entire relation. So remember, in cases where we have small finite things, it's easy to look at the full relation. In general, for infinite sets, it does not make sense because you couldn't write out every element in the relation. So it's better just to talk about them in general. But for finite sets, we can certainly do that. And then we were just asked to write out this relation. So this is just a reminder that we can write out relations, and relations are just sets of tuples where the elements are related to each other through some property. So, yeah, any other questions on writing this out? Does anti-reflexive have the same? Oh, yes. Yeah, I think the book generally uses E-reflexive. But it uses anti-symmetric, I think. So yeah, I just meant E-reflexive. Good catch. Yeah, so let's figure out, so is this relation reflexive? Do we think yes or no? Yeah, no, this is not reflexive. No, so let's consider the element. For example, let's consider 5. That's in the set A. 5's not in the relation. So it is not reflexive. Is this E-reflexive? Yes, so yes, we have some in chat, and yes, it's E-reflexive, so yes. And how do we prove it? Well, let's let A be in the set big A. It's not true for any A that A is greater than itself. So AA is not in the relation. So R is E-reflexive. E-reflexive means for all such A comma A is not in the relation. And this is what we showed. A is not greater than A for any such A. What about symmetric? Is this relation symmetric? Yeah, so we have some people typing in chat. No, and that is perfect. This is not symmetric. No, so let's just do a brief counter example. 5, 4 is in the relation, but 4, 5 is not. Thus, it's not symmetric. Is this anti-symmetric? Yeah, so some people typing in chat, yes, it is anti-symmetric. So let's show it. So let's let A, B be in the set A, where A is not equal to B, and A is related to B. Then we need to conclude B, comma A is not in the relation. That's just what it means to be anti-symmetric. So then, by definition, since A, B is in a relation, A is greater than B. Thus, it is not true that B is greater than A. So B comma A is not in the relation. Thus, it is anti-symmetric. What about transitive? Is this relation transitive? Yeah, so some typing in chat, it is transitive, and that is correct. So yes, let's let A, B, C be in the set A. And right, A, B is in the relation and B, C is in the relation. That we need to conclude that A, C is in the relation in order to prove it's transitive. So then A is greater than B and B is greater than C. Thus, A must be greater than C. So AC is in the relation. So R is transitive. Yeah, perfect. Yeah, so this is it's a simple problem, but the thing to remember here is that we talk a lot about these relations that are finite, but remember we can also, for small sets A, we can write out relations. We can just look at the elements written out and determine whether or not the relation has these following properties. So any questions on this? How long should a problem like this take during the quiz? A problem like this, I don't know, tough to say just right off the top of my head. Probably looking in the range of 5 to 10 minutes. 10 minutes being the max, probably a little bit closer to 5 to 8, maybe. Only just because some of the explanations are a little bit long here. If this problem just instead just ask yes or no, and if no, then just explain why it should be a little bit quicker than that. I guess I went through the explanations. I guess I went through the explanations for why these things hold. So for transitive, anti-symmetric, and irreflexive, I guess the way that this problem is phrased, you would just need to say yes and not prove that it's true. So I guess in that case, this should probably take about 5 minutes. but it's a little bit hard to judge. You should hopefully feel like you have the quiz shouldn't be as difficult as it was like the previous time. But yeah, probably about 5 minutes if you don't add in the explanation for the yes answers. Awesome. So let's take a look at another problem. So we've got that as a equivalence relation. Let's take a look at sure, let's take a look at this one. So here we've got another function problem. So we've got a function from the integers to the integers, and it's defined that f of x is equal to x cubed plus 1. And then we need to figure out if it's one-to-one or onto. And then if so, we need to prove it. If not, we need to give a counterexample. And then based on that, we can figure out if f has a well-defined inverse function and what that would be if it does. So I'll give you a few minutes to think about it. And then we can walk through it. All right, so do we think that this function is a one-to-one function? Let's tackle that part first. Yes, we have some thinking that it is in fact one-to-one, and yeah, that's the right intuition, because we're using we have a cubic function here. It will be one-to-one. Remember, we can think about one-to-one in graphic sense as kind of being a horizontal line test, similar to like a function. You have a vertical line test. One-to-one is a horizontal line test, where if a horizontal line passes a function through more than 2 points, or through 2 or more points, then it's not one-to-one. So yeah, that intuition is right. So let's try to prove it's one-to-one. Does somebody want to walk me through how we would prove that this is one-to-one? We've gone over this quite a bit. So someone want to give suggestion for how do we start proving this is one-to-one? Yes, somebody says let f of a equal f of b. Yes, so first, but before that, first, let's let a and b be an element of z of our domain. And we can assume that f of a is equal to f of b. The reason why we just want to make sure that we're only looking about stuff in the domain. Sometimes you will, depending on how the domain is defined, you may have a function that you think is not one-to-one actually become onto one-to-one. As a brief aside, an example of that would be f of x equals x squared is one-to-one if f is defined from the naturals to the naturals. Because x squared generally looks like this, right? And you'd be like, oh, no, that's not a one-to-one function. It doesn't pass the horizontal line test. But if we restrict the domain and codomain to this portion of the graph and we ignore this portion, then it is a one-to-one function. So just always be remembering what your domain and codomains are whenever you're proving these. So we need to define AB to be in our domain. FA equals FB, so we have FA equals FB. Definition, you applying the definition of the function, so that means a cubed plus 1 is equal to b cubed plus 1. So a cubed equals b cubed. And this means that a equals b because it's a cubic function. If this was a square function, we couldn't get that result, but because it's a cubic, we can conclude that a equals b. Thus, f is one-to-one. Any questions on proving it's one-to-one? Awesome. So, oh yeah, so why did you say it's not possible with quadratic? Oh, sure. So, well, in general with the quadratic, the issue you have is that, like if we had, for example, a squared equals b squared, we could conclude that you could have the case where a is equal to this happens either when, how do I want to describe this? Basically, you can have right negative a squared to be equal to a squared, but a squared is also equal to a squared, and negative b squared is equal to b squared, and b squared is also equal to b, or b is equal to b squared. So because you have these possibilities of positive and negative, it could have been that a was negative and b is positive, and the square of them could be equal, but the values are not equal. For example, 2 squared is equal to negative 2 squared. Both are equal to 4, but 2 is not equal to negative 2. This is in general. If your domain and codomain are different, for example, over the naturals, this is fine, because it would be impossible for you to have had the negative one, because that wouldn't be into your naturals. But in general, if you were over, say, all the integers, you couldn't conclude that with a quadratic or any power of 2. So quartic wouldn't work as well. So in general, for even functions, we can't, but for odd functions, we can. So now let's think about onto. Do we think that this function is an onto function? So in other words, do we think that for every element of the codomain that there's an integer that maps to it? And yes, somebody says no, and that is kind of the right idea. For this one, this is not an onto function. So we just need to find some point where we have an integer in the codomain that is not mapped onto by an integer in the domain. So does anyone have any counterexamples to show why this is not onto? So somebody says 7. So yeah. So let's take a look. So no. So let's consider 7, which is an element of our codomain. If 7 were mapped onto something, then 7 would equal x cubed plus 1 for some x. We don't know what x is in yet. And then if we solve this, we'll get 6 is equal to x cubed. And thus x is equal to the cube root of 6, which is not an integer. So we found some element in our codomain. It's not mapped onto by an integer, so it's not mapped onto anything in the domain. So thus, f is not onto. And there are many such examples. For example, 3 would also not be mapped onto by anything. 4 also would not be. 5 would not be. So many such examples for this function to show that it is not onto. So then, does this function have a well-defined inverse? Yeah, no. This function does not have a well-defined inverse. It is not both one-to-one. And onto. So any questions on this problem, on the part about onto or why this function doesn't have an inverse?
So in general, it's not going to have an inverse if it's not one-to-one and onto.
Yes.
Okay.
Yeah, so you have to have it has to be one-to-one correspondence. So it has to be both one-to-one and onto. So have an inverse. The wording well-defined here was just meant, yeah, I guess we could have just asked, does f have an inverse function? In this class, we assume all inverse functions are well-defined, meaning that they are indeed functions. In some textbooks, it's outside of the scope of this class, but there are some textbooks that consider certain partial inverses, but that's not important right now. So I should have said, does f have an inverse function? So well-defined, not important. Is there any way to prove it, or should it just be one-to-one correspondence? Yeah, it's just a one-to-one correspondence is the reason why. So in one of the lectures, we talked about a theorem that says if a function is both one-to-one and onto, then it has an inverse. And that goes both ways. So the function has an inverse function, then it is both one-to-one and onto. But be careful if you want to prove. So for example, if you wanted to prove a function was one-to-one and onto, you could prove that the function has an inverse, but be careful down that road, because you often have to be very careful with how you look at the domain and codomain to determine if the inverse you have found is actually well-defined. So it's actually a function, maps every element from the domain to the codomain, and is indeed the inverse function. So just be a little bit careful if you go down that road. because you just have to be careful with how you look at the domain and the codomain when you're looking at inverse function. If you wanted to try to sidestep a proof on one-to-one and onto-ness by proving the inverse. Just be very careful if you wanted to try to prove it that way. I'd recommend not. I think directly proving one-to-one and onto is generally the easiest way to prove something is one-to-one correspondence. But proving it has an inverse function also would suffice. So we have about 7 minutes left. So I guess, are there any last minute questions anybody had over the material? Or really anything that might be on the quiz? So any definitions or any problems we've gone through or concepts you just want to hit right before we're about to go? Okay, so somebody said, can you go over really quick what we'll be on? So it'll just be on functions and relations. And so very similar problems to what we have been seeing in lectures, discussions, and recitations. So, right. So all of the stuff about functions. So, you know, if something's one-to-one, if it's onto, inverses of functions. We also had like composition of functions. We had like arrow diagrams to draw out functions. And then we had relations. We also had, so we had arrow diagrams for relations. We have reflexive and irreflexive. Symmetric and antisymmetric. We have transitive, whether something's an equivalence relation. And then we have the partial orderings, strict orderings, and total orderings. We also have relation composition. Relations can also have inverses. For relations, we also talked about and went over today like a Hasse diagram if you had a partial ordering, etc., etc. This is just off the top of my head, so don't like consider this exhaustive. But these are the things. I mean, the big ones, certainly, you need to know one-to-one onto inverse. 100%. Certainly, you need to know reflexive, irreflexive, symmetric, antisymmetric, transitive relation, equivalence relations. Those are super important. So I can nearly guarantee you will have questions over those. The rest of this, you should definitely still know, and be prepared for questions that might be over orderings or compositions, et cetera, et cetera. It's basically just everything we've talked about in lectures, and then problems very similar to recitations and discussions. So I'd make sure, the one thing is on this quiz, there's a lot more definitions and things to remember, such as what one-to-one is, onto is, inverses, compositions, all the reflexive, irreflexive, symmetric, antisymmetric, transitive relations, all the orderings. So make sure you have those, definitions. If you still can't, remember you have trouble sometimes, have those on your note sheet, all of those written out, just so that you remember all of those. Yeah, so that's what mostly, there may be some other things that we've talked about in lecture that I'm not remembering right now, so don't think this is exhaustive, but these will be the main things. Somebody said, can you go over, is the quiz going to have about the same amount of questions as the practice quiz, or will there be more? No, there will be less than the practice quiz. The practice quiz had like 9 or something. I think it'll be fewer questions, and it'll be a similar number of questions to what we've seen in previous quizzes, but hopefully the questions will be a little bit shorter than what you've done, especially for the last quiz, because we've tried to take into account some of the complaints that we got on the last quiz being a little bit too long and taking a bit too much time. So this one should be shorter. So the problem should hopefully be a little bit quicker to solve. Any other last minute questions? Real quick question, what does composition mean in function and relations? Great question. So let's talk about relations first, I guess, because it generalizes to a function, because a function is just a relation. So with relation composition, right, we have that. So let's just say we're given some A, B, and C. If a C is an element of R2 composed R1, note the ordering of this. If there is an element B such that AB is in R1 and BC is in R2. So remember that the relations, when you're looking at the composition, it kind of works just a little bit backwards, right? Because it's R2 composed R1. So you look at R1 first. Is there an element B where A is related to B in R1? And then is there an element B related to C in R2? If it is, then AC is in your composition. And then remember, for like function composition, it works the same way in regards to what you're looking at here with relation composition, because functions are just a special type of relation. But we generally think about functions in the way such that f composed g of x is f of g of x. Notice here we do the function g first, like we do in relation composition. We evaluate g first, and then we evaluate the function a, or f, which is what we do in relations. So that's just very brief, just remembering how that composition function works. Awesome. So we're at time then. So good luck on the quiz tomorrow. Hope you all do well. There was another review session earlier today that's on the YouTube channel. So if you wanted to see some more examples, I think they went through some different problems. So if you still have some questions, you could check that out. Otherwise, I hope you all do very well tomorrow.
Thank you so much.
Yeah, no problem.